This video goes a bit deeper into event studies. We will introduce some notation and derive the statistical properties of abnormal returns. Abnormal returns are deviations of observed returns denoted Ri tau during the event window from normal returns or expected returns. Let's introduce some notation to describe different concepts of time. We use the calendar time t, which is often also used for the estimation window. In a previous video, we discussed the concept of event and estimation windows. Event time refers to the Greek letter tau, where tau is equal to 0 indicates the event date. That is, the exact time of the event. Event time is expressed relative to the event date. Hence we might have tau equal to -2, -1, 0, the event date, 1, 2, and so on. Note that we assume that an event is exogenous in the sense that market prices do not trigger the event. Hence, one has to be careful with events such as defaults, as a drop in share price might trigger financial distress. We use an estimation window to derive the parameters needed to determine normal returns. As discussed, we can use a market model or a constant mean return model. Let's focus on the more common market model. We can write the market model as expressed in equation 1 on the slide. So the stock return, IT, so for company I at point in time t, is equal to a constant term, alpha I, plus a beta coefficient, beta I, RMT, which refers to the market return, so that's the return of a market portfolio, plus a random error term, epsilon IT. In the previous video, I spoke about the underlying assumptions we make. In this case, stock returns follow a multivariate normal distribution. Now this is quite a strong assumption and will be used later to derive statistical properties for the abnormal return. Equation 1 is estimated using ordinary least squares, OLS in short. The estimation happens during the estimation window, which is away from the event window. It's usually before the event window, sometimes it could be before and after, as discussed in the previous video. Now OLS provides estimates for the alpha I and the beta I. Note that these parameters will differ between stocks I. It is common to express equation 1 in matrix form. A matrix or vector is indicated using a bold font in print or using underline on a whiteboard. I have done a couple of videos in my playlist on applied mathematics for data science to go a little bit further into matrix notation and linear algebra. So if this is not your strongest area, have a look at the playlist and enjoy. It might be useful to look at equation 2 and illustrate the patterns on the whiteboard. Let's start by writing down the original equation for our market model. So return RIT is equal to a constant term plus the beta coefficient times your market return and then our error term. Now I would refer in this case to our cross-sectional dimension. So I just put a comma here and just state that I is running from 1, 2 up to capital N, and time would be maybe an estimation window running up to maybe say capital T. Yeah, so that would be our estimation period. Now I can express this equation in a matrix format. Now what we note is that our coefficients differ between stocks I, but not over time. So they are constant over time, that's the assumption we make, but they differ between different stocks I. So let me now just rewrite this a little bit, focusing on the time dimension. So I look at this for different stocks over time as follows. I2 and going up to capital T. So I look at stock I and run through time. So this here becomes a column vector. Dimension T, the number of rows with one column. It's a column vector. Then here on the right hand side I have the following: alpha I plus beta I. And now I have here a vector for my different values of the market portfolio. So it runs from 1 up to, again, capital T. So I obtain here another column vector. Now, of course, to match, in this case, my structure, because this is a T times 1 column vector, so I have to maintain the same structure. This will need another vector of all ones. I just use 1 here underline. Now this 1 underline would have the same dimension to match it, so it's a T times 1 dimension. Because the alpha I is just a number, it's a scalar, so I have to match the dimensions, otherwise I can't add these different vectors. So if you want to write this out, we can do this in a minute. And then I shouldn't forget I have my error term. Now it's a little bit messy here. Let me just get a bit of space, which refers to epsilon I1, epsilon I2, up to epsilon I capital T. So again, it has the same dimension. It's usually helpful to write down these dimensions and make sure they actually match. I will do a few more videos on matrix notation, bit about linear algebra needed for data analysis, data science, and I will put this into my playlist focused on applied mathematics. So if you want to know more, have a look. It will be highly exciting. So this little term here is the all one vector. Yeah, so running all the way up with a matching dimension of t times 1. And when you look at this structure here on the right hand side, so this structure, we could simplify this now using matrix multiplication, and I do this in the next line. So I can simplify the notation as follows. I obtain the vector Ri, which is exactly the vector above. Yeah, has this structure we saw. It's a column vector of dimension t times 1. And on the right hand side, I now will simplify this expression. So you see you have the all one vector, and then you have the vector for the market return. And we can put this together into one matrix. This matrix is also called a data matrix. Yeah, so it's often referred to as a data matrix. So here we have the all one vector, and we have our returns for the market portfolio, again going all the way up to capital T. So that would be the structure, basically combining these two vectors. And then I can put my parameters into a parameter vector. And I'll talk about this in a minute, and you will hopefully see that this is matching. And then finally, the error term will be combined into my epsilon I vector. So that's the column vector you just saw above. Now, matrix multiplication works based on the first row, first column principle, and then it continues. So what you do is you multiply the first row and the first column, and then you move to the next one. And this gives you again the same structure. It will be a t times 1 structure. So you would obtain alpha I plus beta I times Rm1. And then in the next row, you would get alpha I plus beta I times Rm2, and so on. Yeah, so it will be just the same structure you saw above. Yeah, so you have all the alpha i's put together because they are multiplied here with the all one vector. And then you have the beta I times the respective market return for the different points in time. So this basically gives you exactly the expression above. Now let me have a quick look at the dimensions. So we already noted in terms of dimensions that the column vector on the left hand side is t times 1. We know this is also t times 1. Obviously this is now a column vector which is 2 times 1. I have 2 rows, 1 column. So here I have in total t rows and 2 columns. So if you do a multiplication, you have to make sure that dimensions are matching. So this dimension here has to match with this dimension here. Yeah. So always look at these dimensions that are adjacent, make sure they match. And the resulting vector takes the 2 outer dimensions. Yeah. So you would take this one here and that one here, and you would end up with a dimension as intended of t times 1. So the last step is we simplify this notation wise. So I end up with my I vector is equal to, now I use the x vector, so this is my data matrix, this is a very, very common notation, times theta vector I, where the theta vector exactly stands for my alpha I, beta I. So this is basically my parameter vector plus the error term. Yeah, and the power of matrix notation is I can express this system of equation here for all the different i's, all the different stocks in a single line, which is very powerful because also computationally, this is basically exactly how it would work. Yeah, so if you want to translate this later into a statistical software, you could code based on this equation depending on the programming language you use. This in particular refers to a Metricsbased programming language, which is common in the case of Marta, which belongs to the Stata package. You have the same structure, of course, you have in data frames. So if you're used to pandas data frames, you have the same structure. So as a matter of fact, this data matrix here corresponds with what you call an array in a programming language. Yeah, so this is quite a nice connection between your notation and how you could implement this later in code. Now, estimating equation 2 with OLS yields the point estimates and the following covariance metrics expressed in equation 4. Equation 3 is the standard OLS estimator. I can cover OLS estimation in additional videos. It's not the focus here. Notation-wise, you note the transpose. So this is simply the prime in this case. So x prime is the transpose of the data matrix. The -1 indicates the inverse of a matrix. All of these different elements, of course, are very basic building blocks used in matrix notation and in linear algebra. Expression 4 is the covariance matrix of my parameter estimates. Have in mind that whenever you estimate this equation, the estimate is never ever precise. Yeah, so we always obtain a distribution here. So basically what you obtain is you hopefully hit somewhere here the true parameter theta with your estimate theta hat. But you will wobble about this, so you have a distribution around the true parameter. You have to, of course, impose all else conditions, and then you end up with the equations 3 and 4. And also you can say something about the distribution of my estimate. In this case, you would assume, as long as all the assumptions are met, that your expected value of your estimate will correspond with your true parameter theta. We will actually use this a little bit later. And we have a variance as expressed in equation 4. The whole distribution then would be a normal distribution. Also note that the last term here, this is our error variance. Yeah? So this will tell me something about how good is in fact this model fit for my normal return. Abnormal returns refer to the observed stock returns during the event window minus the expected stock returns based on our model of normal returns. So in our case, we used a market model, but we also spoke about a constant mean return model, which is just a simplified version of it. You just set beta equal to 0 and you are in a market model. So equation 5 exactly describes how I obtain abnormal returns. I look at my observed stock return in the event period denoted tau. I then deduct my expected return. So that's the deviation from the expected return based on the market model. Note that the parameters were estimated during my estimation window. So that's during a different time period. And I use the current market return in the event window. So I use the notation Rm tau to refer to the event window. Again, I can rewrite equation 5 in matrix form. And here the asterisk refers to the event window. Now the event window will usually have a different dimension, so I use later the dimension t prime for the size of my event window. So put differently, I can exactly use the same logic to get to expression 6 from expression 5. Now, from 6, we can derive the statistical properties of abnormal returns. These properties should hold under the null hypothesis. The null hypothesis states that the event does not affect the firm's market value. So how do we proceed? We take conditional expectations of equation 6 and derive the covariance matrix given that we observe the data matrix. Again, have in mind the data matrix contains the constant term and the observed stock market return, so the return of a market portfolio during the event window tau. Let's move again back to the whiteboard. So let me start with equation 6. So we have our abnormal return in the event window. So I use the little star to indicate this. It's an estimate, so I put a hat on top. And this will be stock specific I. So notation now gets a little bit wild. I look at my observed return. So again, that's during the event window. So that's a time dimension here. So if I want to fix dimensions, it would be t prime 1 and so on, minus the expected return. So the expected return refers to my data matrix, and we saw this before, again in the event period, times the parameter vector, which I estimated during the estimation window. So again, thinking about dimensions, I would have a true one here, have two parameters in the case of a market model, and here I have to match the two, and it will be a t prime. Yeah, so again, you end up with t prime 1 if you multiply this out. So that should be about right. So now things are getting a little bit dicey, and most likely I will make lots of mistakes. If I do make a mistake, yeah, just let me know in the comments. Of course, I always make mistakes in a deliberate fashion to ensure that actually people pay attention. Well, I claim that. Let me claim that. Okay. So what we now do is we take conditional expectations. Now, but what does that mean? It means that my condition is basically what I observe. So I can treat whatever I observe as something I know about. Hence, something I know about can be treated like a constant term. So it doesn't have any variance. It's a constant. So observing the data matrix means I observe my stock market return in the event window. And then I just apply this to my equation. I just write it down first, and then we think about this a little bit more. I might sometimes forget to underline, but you notice that in fact all these different terms are referring to a matrix or a column vector. So it should be clear based on the context. I try to pay attention, but sometimes it might slip. Now, what I do next is I follow what you see in Campbell-Low-McKinley and just add a few terms, subtract a few terms. Is just to basically visualize what's going on here. It's not always perfectly necessary, but you will see in a minute what I mean by this. So I end up with an expected value as follows. I now use rectangular brackets. I have my vector of observed stock returns, and now I deduct here my data matrix, but I use the true parameter value. Yeah, so you might ask now, where is this coming from? It wasn't there before. Well, it wasn't there before. I just put this in, and I have to, of course, add this back to balance out the equation. So I can add this back in the second term, and I can move out my data matrix. I just multiply this out, and I end up here with theta 1 hat minus theta. Yeah, so just like that, given my data matrix. So now notice, because I have conditional expectations, I can treat this data matrix just like any other constant term. I have here the expectations operator, and expectations operator is a so-called linear operator. So certain properties apply. Yeah, in particular, if I have a constant term, it just can be moved out of an expected value. Yeah, so if you have an expected value of a times x, where x is a random variable, a is a constant, it's simply a times the expected value of x, and so on. So again, if you're unsure about these properties, let me know. We can always add a few more videos on these very joyful and exciting topics. So looking at this a bit more carefully, what actually is going on here? So this first term here actually is an expression for a normal return. Yeah, so that's an expression for a normal return. So that here would refer to epsilon I star, yeah, without the hat. So that's basically the error term coming from a normal return equation. Now again, notice that the theta in this case here is the true parameter vector. So that's not the OLS estimate. Yeah, the estimate is the one here with a little hat. So if we assume that our method to determine normal returns is correct, so all the assumptions hold, so if we make this assumption, we would be able to argue that the expected value of this error term in my normal return model, given I observe my data matrix, is equal to 0. Yeah, so this is standard assumption if we assume there is nothing going on in terms of endogeneity, blah de blah, so we are well specified, then this has to be the case. So what you notice very quickly is that what we do in terms of deriving statistical properties implicitly always assumes that our normal return is well specified and all our assumptions hold. Now in here, so if you want to derive this, we again note that the first term is a constant, so that's just a constant, so we can just pull this out and I get an expected value of the second term. Now the first part here is our OLS estimator. Yeah, the second part is a true parameter value. So as long as we are unbiased, and again, if you're not sure about this term, let me know. So if the estimate is unbiased, which we would assume if OLS assumptions hold, then this term would vanish. Yeah, so on average, I'm not systematically wrong. Well, this is the property of OLS, so that should be fine. So summing up, I end up with a term which is equal to 0. Yeah, so moving all the way up, we can argue that our expected value, if of course all these assumptions hold, of our abnormal return, given we observe the data matrix, should be equal to 0. Good, let's move to the covariance matrix, and now things get a little bit more wild. So first of all, it's useful to note the following on a variance. Now, just in a very general way, the variance of a random variable set can be written as the expected value of set to the power of 2 minus the expected value of set and outside to the power of 2. Now this equation you can easily derive from the basic definition of a variance, which is set minus expected value of set power of 2. Simply the central moment. So basically from this you can easily move to this line. Yeah, so if you're unsure about this, try this at home and it should kind of work out. Yeah, it might take a while. You just have to be patient and apply standard methods. Again, noticing that the expectations operator is a linear operator. So we already spoke about our expected value. So when we apply this equation here to our term, so if we look at a covariance matrix of my epsilon hat star I underline, given the data matrix in the event window, so if I look at this covariance matrix, I apply the same principle. So I end up with an expected value of something to the power of 2. And in this case, if you have a vector, something to the power of 2 can be written as follows. And I will justify this in a minute. It's simply taking here the transpose of the second term. And you will see this in a minute. And the second term is simply the expected value, which we just discussed. Yeah, so I'll write it down one more time. We just spoke about this expected value, and we argued that, of course, if everything holds, this is equal to 0. So it would drop. So we only focus here on the first term to talk about the covariance. Now, why is it actually a covariance? How do I immediately see that? Well, we have to have a little look at this expression here. And whenever you get confused with matrix notation, the best thing to do is simply just, take your time and write it all out. And usually it becomes much more apparent. So let's just write this out. So the epsilon I star little hat is a column vector running through my event window. So for instance, it might start 2 days prior to the event, and then it goes 1 day before, and then it might be the day of the event, and so on. Yeah, and it might continue for maybe another 2 days, say. So that would be the structure. So we have here t prime times 1, so that's the dimension. So if I take this column vector, what can I say about this product here? Let's have a little look. So if I look at the epsilon I star hat epsilon I star hat prime, I have exactly the same vector I saw before. So I have here the epsilon minus 2I hat blah blah blah, and I go all the way down maybe here to plus 2I, so 2 days after the event. And then of course it's a transpose. So the first term of course is my column vector, so I would have dimension t prime times 1. The second one would be then a transpose. A transpose switches my dimensions, so I end up with a row vector. So it would be 1 times t prime. Yeah, so it would be simply my epsilon hat minus 2I all the way up to epsilon 2I hat. And then you just apply the rules for matrix multiplication. So first row times first column and so on, and you end up with a matrix where you simply multiply this all out. So I get a term like epsilon hat minus 2I power of 2, and then I have lots of these cross terms. Yeah, I have all these cross terms and so on and so on. And on the main diagonal of this matrix, I get these terms to the power of 2. Yeah, and so on and so on, and it goes all the way up to maybe 2, blah, blah, blah. I shouldn't forget the hat here, power of 2. And then all these other cross terms, yeah? And we have to think about these cross terms. Now, that of course depends on your underlying assumptions, yeah? But we would usually assume IID distribution, so the cross terms tend to vanish under our assumptions. Now, if you end up with this, you have a structure of T prime, T prime. So that gives you an expression that measures the covariance structure, or as a matter of fact, you look at one stock in this window of time. You would assume that over time your error variance should not change. You would assume that. So it would be assumed to be one error variance, and you would also assume that you don't have any autocorrelation over time. So all these terms which are not on the main diagonal of your matrix should vanish after you apply the expected value. Yeah, so that's the focus here. So it should simplify accordingly once you impose your assumptions. Let's look into this a bit more carefully. So let me just now write it all down. So I do now this conditional variance. As we just saw, the focus will be as follows. On this term, I just now use rectangular brackets. It gets very wild very quickly. Epsilon I star hat, conditional expectation observing my data matrix. So that's basically what I do. And let's now just write it out. So what we have here is I just put in now for my abnormal return the equation. So the first one is simply the abnormal return. So it's my my observed return in the event window minus my expected return. So that depends, of course, on my observed data matrix times the estimated parameter vector. So this is what I obtain. And then I have this going on in the second part. And here I have to use a transpose and have to then apply here the conditions. I apply the conditions. And now what I do is I just simply follow our standard definitions. Yeah, so again, I use something similar you have seen before. So I will replace the return. So I replace the return here with my normal return expression. So I obtain here my normal return using the true parameter value plus my random noise. Yeah, so that's basically, that comes straight from my market model. And I include this here in my equation. And I just then rearrange and multiply it out. And now it gets messy. That's the thing, it really gets messy very quickly. But you have to just be patient, and most likely, you will make lots of mistakes. That's what it is. So we end up here with epsilon I star. So note it's not the head, so that's not my abnormal return. So this is based on my normal return model. And then I can put the data matrix out. And in here I have my theta hat minus the true parameter value. So that's the first term, and then I have the second term which exactly looks the same. I just put here my transpose. So that's this monstrous equation. And then we basically multiply this out, and we have to notice one thing here with the transpose. Now, the transpose works in the following way. I might just illustrate this here. So just as a little note on the side. If you have a term A, this might be a vector term, matrix, whatever, plus BC transpose. Yeah, so what happens is, if I apply the transpose, I get A transpose plus BC transpose. And if I want to apply the transpose for the product here, I have to switch them. Yeah, so you get C transpose, B transpose. Good, so let me just then get back into it. Again, if I make any mistakes, which is quite likely, I haven't had enough coffee today, let me know. It's very easy to do, and it's getting a little bit messy on such a whiteboard, in particular because you don't see everything in one go in a straightforward manner. Good, so now what I do is I basically start multiplying everything out, and you get lots of these cross terms, which anyway will drop under normal assumptions. Yeah, so you end up now with the first term, and if you go up here, the first term is this epsilon I star prime. So that's the first term here, and then you get quite a few cross terms. Yeah, so I will just kick this out for the time being, because these cross terms are all equal to 0, and this is simply because our normal return function or normal return model is correctly specified. Yeah, so you don't have there is no endogeneity, nothing funny going on. So if you take an expected value of an error term times something else, this expected value should be equal to 0. Yeah, so this is just, it's pure random what you get in the error term. So that's basically it. And then here in the back you have another term which has a value, so it's xi star, and then you have the expression for the estimate of my parameter vector and the true parameter vector, and then this multiplies with the same transpose and then times xi star prime. And then I should not forget I have here conditional expectations. Yeah, so I have to do something like this. Now again, note because of conditional expectations, when you look at the second term, these are constants. Yeah, and actually, if you have this in a vector form, this is a data matrix, yeah, a matrix form, you end up with something power of 2 and some cross terms, basically. This is what it is, but this can be treated like a constant. Again, you have an expected value applied, so you can actually move these constants out, and you can apply an expected value to the term inside. And when you look at the term inside, what you have is, you have an expected value of something to the power of 2. Yeah? And that is nothing else but a variance term. Yeah, so this here is basically the variance, or be precise, a covariance matrix of your parameter vector, the estimate of it. Yeah, so this is basically standing here. And that simply follows from OLS, because we know this term already. This is OLS. And again, if you are unsure about OLS, I can, that wasn't intended. I can do a few more videos on that. So you have here a data matrix, prime, data matrix, -1, and then the error variance, epsilon I. Yeah, so that's the error variance here. So that expression comes simply, this is simply OLS. Yeah, so what we have here is simply OLS, and the constants are just multiplied into it. That's all it is. Yeah, the first term we already saw the structure. Yeah, so you get this covariance matrix. I already mentioned that if, of course, assumptions apply, you end up with the same constant variance, and all the cross terms, so there is no autocorrelation, will drop. So if you do this in a matrix form, because here you note that it's t prime times t prime, you end up with the identity matrix I times sigma square epsilon I. Yeah, which is the constant error variance, which differs between different stocks. Once on the main diagonal, everything else is 0. Yeah, so that's the identity matrix. So that's basically it. So you end up with a variance term which combines here an identity matrix and the error variance, which is constant over time. And then you have here some weighting happening based on the current value of your data matrix in the event window times the normal OLS variance term. Good, so that's it. And in the end, if you combine all the results, you end up with the expression in equation 7. Yeah. Again, this is what you see in the book I discussed. So this is Campbell-Low-McKinley. So this distribution, of course, should be expressed as a conditional one. So given you observe your data matrix. Yeah, this is always what we argue. This is not very clear in the book, but that's basically, I assume, intended here. So the abnormal return vector. So this is the vector, as you can see, in the event window. Yeah, so if you go through the event window, you would assume that you are having a normally distributed random variable with an expected value of 0 and the covariance, which we just saw. This, of course, would be assumed under the null. So assuming there is no systematic deviation from the expected or normal return. Now, equation 7 can be then used to derive the test statistics in event studies, which we will cover in a future video. So I hope you enjoyed that. Now it's time for a little break, and I'll see you in the next one.